This video is going to be a tutorial on free body diagrams, okay? We'll write that up here, free body diagram. Okay, a free body diagram is basically just a picture with very careful depictions of all forces, all force vectors that are acting on an object, okay? So you have to look at a picture and decide what are all the forces acting on an object, okay? Write those forces as arrow vectors on the picture, and that makes it very, very easy to solve any force problem that you could possibly come up with, okay? So there's 3 examples on this slide that says free body diagrams, okay? And we'll go one by one and explore what the free body diagram would be of that object, okay? The very first one is a little possum guy, right? So he's got this, here's like a branch, right? And then he's got his little tail, right? And then there's like a little possum, okay? All right, make it look like he's actually like some kind of a creature. All right, what are the forces acting on this object? Well, we have gravity, right? It has a weight, so I'm going to call that W. Okay? And we know it must have more than just its weight, otherwise it would fall to the ground. It would start accelerating downwards, right? So what's holding it up? Well, he's got this little tail, and anytime you have a tail, that's a tension. Anytime you have a rope or a chain or anything that's holding you up by like a dangle, okay, that is going to be called tension. So I'm going to put a T there for tension. Okay, does that make sense? Is there anything else? Well, maybe there's a breeze going this way or that way so that there's like some sort of wind load or air resistance, but it doesn't look like it in this case. Really, it's a simple situation. He's got a weight going down and tension going up, okay? Now, the cool thing about this is we could say that the sum of forces equals ma, right? Because we have such a clear drawing, I can say the tension minus the weight must result in the mass times acceleration. And now I have a little equation that I can analyze the motion of this little critter. Okay? All right, that's why we do this. We can just read the forces right off the picture, turn it into an equation. Okay, let's do it over here for this fellow running, right? So we have, I'll do the best I can here. We have this foot, okay, this ankle. All right, and then he's like got another foot here. Well, that's not a foot, that's a hand. Okay. And then he's got another hand over here. This actually is not terrible. I'm really kind of impressed with myself. He's got a weird head, but everything else looks good. And that his stomach's missing. Okay. All right. So, well, what's going on here? Here's the deal, guys. There's a couple of forces going on here. First of all, again, the dude's got his weight, right? The dude has a weight. So gravity's pulling him down this way, right? The other thing is that if he's in contact with the surface here, right, the surface has to be pushing back on him up so that he's not falling through the ground. So there must also be a normal force here going upwards. I'll call that N. Okay? Now, that's everything that's going up and down, right? So we know that in the y direction, we can say that N minus W equals his mass times acceleration, but he's not going up or down, so this would just be 0, right? N minus W equals 0. In this case, the normal force would have to equal the weight, right? But what's propelling him forward? This is a really interesting question. Why does any runner actually move forward? Well, here's the thing. This guy his foot is pushing off the ground this way, right? He's pushing back on the ground, right? But according to Newton's third law, for every action, there's an equal and opposite reaction. So that means some force must be pushing his foot forward. There must be some force. Can you guess what that force would be? Could he be running if this were ice? No. So it's a hint. That force is friction. Okay? So anytime somebody's running, it's because they are pushing off the ground backwards, right? So he's pushing on the ground this way, but the ground pushes back on him, equal and opposite force this way, and that force is friction. Okay, so this would be the complete free body diagram. In this case, we could say that sum of forces in the x direction must equal mass times acceleration. Well, the only force in the x direction is the force of friction. So that's what's causing his acceleration in the x direction. Okay? All right, lastly, we have a bat hitting a ball. Okay? We have a bat hitting the ball. Okay? But as you can see here, so here's the baseball bat. Looks more like a cricket bat. Oh, this is just terrible. And the ball is over here. Now, in this picture, is the ball actually touching the bat? No, the ball is not touching the bat. So once the ball is no longer touching the bat, there's no force from the bat on the ball, many people would be tempted to say, oh, there's obviously a force in this direction. The answer is no. No, there's not. There's a velocity in that direction, but a velocity and a force are not necessarily the same thing, right? So all that's really acting on this ball is that it still has gravity, right? In other words, weight, right? And it has, let's say that the direction of the velocity is this way. Well, there's, an atmosphere, and an atmosphere causes a drag force. So there also would be a drag force opposite the velocity. Drag force is always opposite an object's velocity, so we would put D here for drag force. Okay? Those are the only two forces acting on that baseball. Okay? So that is a crash course in free body diagrams. Anytime you're confronted with a problem, the first step you should do is draw a free body diagram. Think of all the forces acting on an object, and once you do that, it makes it so easy to analyze the motion because we can turn those pictures into equations.